Hello and welcome back to Mr. Latham's AQA revision session. So today we're looking at P2.4, which is current electricity. So start off with, before we can understand electricity and current electricity, we need to understand what electricity actually is. So for us to understand what electricity is, we first need to go back and look at the atomic structure. So you can see here we have an atom which consists of a nucleus which contains the protons and neutrons, and then orbiting around the outside you can see these little specks which represent the electrons. Now electricity is just the movement of charge, and most of the time the charge that we're talking about which is moving are actually electrons moving. Okay, and that is something I want you to keep in mind when we're talking about electricity. It is the flowing or the moving of charge, more specifically electrons for most cases. So, static electricity. So what is static electricity? Well, static electricity is electricity that is held in an object. Now, the types of objects that can hold static electricity are insulators, so plastics are a good example of this, and other non-metals, but also conductors, so things such as metals can actually hold electricity, so they can become statically charged, but this is only when they are not earthed. And this is very important to remember, that they're not earthed, because if they are earthed, then the charge is able to flow to the earth and therefore discharge. So how does something become statically charged? So how do we get static electricity? Well, how we get it is because, and how it happens is because of the transfer of electrons. And it is very important to remember that it is the electrons which are moving only. So when electrons are transferred from one object to another, so there is an imbalance of charge, then we say that the object is statically charged. So a good example for static electricity is a Van de Graaff generator. And a Van de Graaff generator looks a little bit like this. And it is something that you may remember from lessons. It is a metal ball which you hold with a hand or any skin. And as the Van de Graaff generator is turned on, your hair starts to stand up. And then if somebody touches you, then you get an electric shock. So how does a Van de Graaff generator work? Well, a Van de Graaff generator works by having an insulator, or should I say two insulators, down here. And the two insulators here are a felt pad and a rubber belt, which runs around here through this belt system. Okay. Now when the Van de Graaff generator is turned on, the belt moves around like this, and as it moves around there is friction between the felt pad and the rubber belt. And this causes the transfer of electrons, which therefore causes the belt to become electrically charged or statically charged. This charge then moves up the belt until it reaches the top, and then the static charge is then transferred to the metal dome through this piece of metal which connects the belt to the dome. So then when you touch the dome, the static charge is transferred to you. And if you're touching this and you're standing in something like a plastic tray, then you're not going to have an electric shock. And the reason being is because you are, or should I say, you are not earthed. So you are insulated from the ground. However, if you are touching the Van de Graaff generator and you'll become statically charged, and then somebody comes along and touches you, then what's going to happen is there is going to be current flowing from you to the person who touches you, who is in contact with the ground, therefore causing you to get an electric shock. So, other examples of static electricity involves plastic rods or plastic slides or any sort of plastic material, most plastic materials. And how we make these statically charged is simply by friction. So if we have a rod, such as a polythene rod, and we rub it with a cloth, then the polythene rod will become negatively charged. Now the reason it becomes negatively charged is because the friction between the cloth and the rod causes the rod to gain electrons from the cloth. And if you remember back to our atomic structure, electrons are negatively charged, therefore if the rod gains electrons it will become negatively charged. The other side of this is if you have something such as perspex. Now if you rub a perspex rod with a cloth, then you get the opposite happening. So the friction between the rod and the cloth causes the rod to lose electrons. So the electrons are transferred from the rod to the cloth. So the cloth becomes slightly negatively charged and the perspex rod becomes positively charged because it has lost negative electrons. And it's very important to remember that it is the electrons being lost from the perspex which causes it to become positively charged, not the fact that the perspex has gained a positive charge. And because only the negative electrons can be transferred. You can't have any transfer of protons, so any transfer of positive charge. So it's all to do with gaining or losing of electrons. Okay then, so next bit is looking at circuit symbols. So you can see on the slide that we have a number of circuit symbols that you need to remember, and you just simply need to remember what they are and basically what they do. So we'll go from top left to bottom right. So start off with, we have an LDR, and an LDR stands for a light dependent resistor, and it is a resistor, as we can see, because it is a rectangular box with nothing inside. So we know it is a resistor, and these two lines, or should I say arrows, represent light, and light's going into the resistor, therefore it is a light dependent resistor. And these are components that are sensitive to light, and their resistance changes according to the light intensity. And these are used for things such as street lights, so that's why the street lights come on automatically at night, and you can also buy these so you can have lights that automatically come on at night. So our next one is a cell, and pretty straightforward. This is where the potential difference originates. This is where this is the driving force for the electricity, and if we have more than one cell we can call them a battery. So a battery is multiple cells connected together, and just make sure you notice that the cells are aligned the same way. So we have positive, negative, positive, negative. Therefore they have to be wired that way. If you wire them the other way, where we have negative, positive, positive, negative, you would find that there wouldn't be any current flow. Okay. Our next one is a bulb, or more specifically a filament bulb. And it's important we call it a filament bulb and not just a bulb, because there are different types of bulb. You can instead call this a lamp. Okay then, so our next is a switch, which is to stop and start the flow of current through the circuit. Next one is a heater. A heater obviously heats up, it releases heat energy. We have a variable resistor, which is a resistor where we can alter its resistance by sliding a bar and altering the length of the coil, which makes up the resistor. We have a voltmeter, which is to measure the potential difference. We have a fixed resistor, which is just a rectangular box. So this is a resistor with a fixed resistance, so we can't alter that one. We then have this one, which is a fuse, not to be confused with the resistor. You can see that the line actually goes right the way through the rectangle, representing that this is a fuse, and these we'll talk about in more detail on next video, and they are needed for safety reasons. They're to break the circuit to prevent electrical fire or to prevent an electric shock. Alright, now next one is a diode, more specifically a light emitting diode, an LED. So this is a diode which, when electricity flows through in this direction from left to right, it emits light, so it releases light in a similar way to a filament bulb releases light. Our next one is a diode. So it looks the same as an LED, however it doesn't have any arrows coming off it because it doesn't emit light. These are just components which allow current to only flow in one direction. An easy way to remember that is if you look at the triangle, that almost makes a D shape. The line in front makes like an I, and then the circle around it is the O. So D-I-O. It's a little way of remembering the symbol for a diode. Okay, then our next one is an ammeter, which is used for measuring current. And then finally we have this component which looks very similar to a variable resistor. In fact, it is a resistor, but this time it is a different type of resistor. And the way I remember which one this is if you have a look at this line here, it looks a little bit like an ice hockey stick. So when we think of ice hockey, we think of temperature. So it is a temperature resistor, which we call a thermistor. Now these are components that we use in anything which is needed to turn on and off depending on temperature. So things like thermostats in your house use thermistors, any sort of bulbs, any heating structures that you have in a fish tank or in, let's say, a snake viv, all of these have thermistors and they turn the current on and off. So they allow different amounts of current to flow depending on the external temperature or the temperature of the thermistor. Okay then, so a whistle-stop tour of the terms of electricity. So we're going to start off with current, and current is given the letter I, and don't worry too much about that. You won't need to remember that current is given the letter I. It's just something I've just mentioned on here. On the formula sheet they will tell you that current is given the letter I. However, you do need to remember that current is measured in amperes, which is quite often shortened to amps. It is the flow of charge, and the charge is a coulomb. So it is the flow of charge, or the flow of coulombs. And the charge is carried by the electrons usually. However, as I said before, electricity isn't always carried by electrons. It can be carried by ions, such as in electrolysis. But for all intents and purposes, we're going to say that the charge is carried by the electrons. So the electrons flow around the circuit. We say that there is current, and depending on how fast the flow is the current of the circuit. Now the charge is what contains the electrical energy, so these are the packets of energy, and it is this energy which is converted, or in inverted commas used up, by the components. Okay, so the current actually doesn't drop, or the charge doesn't change as it's going through a component. It is merely the electrical energy that is held by the charge which decreases as the current flows through the circuit. And it is measured by an ammeter, and it's very important that the ammeter is wired in series, and we'll look a bit more about series and parallel in a minute. So our next one is calculating current. So you do need to be able to calculate current, and with so many other equations that we have, it is one that they give you on the formula sheet, so don't stress about trying to remember it. But you do need to remember the units. So current is measured in amps, charge is measured in coulombs, and the time taken is measured in seconds. So charge divided by time taken gives us current. So let's have an example. So a charge of 15 coulombs passes through a bulb in 2 seconds. What is the current passing through the bulb? So current equals charge divided by time taken. Our charge is 15 coulombs and our time period is 2 seconds. So 15 divided by 2 gives us 7.5. Don't forget your units. It's asking for current, and current is measured in amps, which is given the capital letter A. Okay then, so potential difference. Now potential difference is also called voltage, although we generally don't call it voltage, we call it potential difference. It is given the letter V and is measured in volts. It is the energy transferred to a component by each coulomb of charge. So if a coulomb of charge is transferring more energy to a component, then we say there is a greater potential difference. It is measured by a voltmeter, and again it is important to remember that unlike an ammeter, the voltmeter is wired in parallel. And again we'll look at parallel and series in a minute. So calculating potential difference. So again, this is a formula that they give you, however the units you will need to remember. So potential difference is measured in volts, energy transferred is measured in joules, and on your formula sheet this is represented as work done. And as with one of the previous videos that I've done, you should remember that work done is an energy transfer, therefore work done and energy transferred are the same thing. So they're measured in joules, and then charge is measured in coulombs. So 32 joules of energy is transferred to a bulb when 8 coulombs of charge pass through it. what is the potential difference across this bulb? Okay, so potential difference is 32 divided by 8. So 32 is our energy, measured in joules, divided by our charge, which in this case is 8 coulombs. So 32 divided by 8 gives us 4. Potential difference is measured in volts, so it is 4 volts. And finally, resistance. Now resistance is given the letter R, a capital R, and it is measured in ohms. And the symbol we draw to represent ohm is this symbol at the top, the omega symbol, which looks a little bit like a horseshoe. Now if you forget in the exam what the omega symbol looks like, you can just write the word ohms. Okay, so both of them will give you the marks if you forget how to draw the symbol. So the resistance is anything that opposes the flow of charge. In other words, it's anything that opposes the current. Now all components in a circuit resist the flow of electrons to some degree, even components such as an ammeter and a voltmeter. And an ammeter is used to measure the current, but even an ammeter will resist the flow of charge to some degree. However, this is very low as to not alter or not to reduce the current as much as possible. Okay, otherwise that would affect the results that we would get when we're measuring the current flowing through any component. And the larger the resistance of a component, the less flow of charge that we have, therefore the lower the current. So they are inversely proportional to each other. So as the resistance increases, the current decreases. Now even wires have some resistance, so we said that all components have them, but even the wires themselves have some resistance, and it is worthwhile noting that the thinner the wire is, or the longer the wire is, the higher its resistance. And a good example of this is a bulb. If you ever look inside a filament bulb, you'll see that there's a very, very thin wire, and that's what emits the light. It is a very, very, very thin wire, and due to the fact it is so thin, as the electricity, or should I say the current, flows through it, because there is so much resistance, the filament gets hot, and it gets so hot that it glows and emits light. And that's how a traditional filament bulb works. And finally, calculating resistance. So how do we calculate resistance? It is resistance equals potential difference divided by current. And again, it is a formula that they give you. You simply just need to select the right formula, but the units you will need to remember. And as with the other equations, resistance is measured in ohms, potential difference is measured in volts, and current is measured in amps. So an example of this is the current through a resistor is 4 amps when the potential difference across it is 8 volts. What is the resistance of the resistor? So we have potential difference divided by current. Our potential difference is 8 and our current is 4. Therefore 8 divided by 4 is 2. So our answer is 2 ohms, or 2 and then the omega symbol representing ohms. Both of these are perfectly adequate to get the marks. You don't necessarily have to write this. If you forget, you can write the word ohms. Okay then, so that's it for part 1. Please like or subscribe. If you didn't like the video, give it a thumbs down. If you did find it useful, then give it a thumbs up, because this gives me an indication as to whether the videos are useful to you or whether they are tripe. So, thank you very much.